Alright guys, you're welcome back to this exercise where we still have one part, which is to calculate the normal and the shear stresses at point B. We have already done that for point A. We have calculated the normal stress and the shear stress at point A, and I told you that the numbers that we got are unrealistic, they are unreasonable. It is my bad because I included numbers that are not realistic. Usually you're gonna end up with very much smaller numbers than we got in the last video. Anyway, so I don't care really about the numbers. I care about the process. I care about the steps that you have to follow for finding out the normal and the shear stresses at any point in the cross section. Alright, so now let's continue with the step 7, which is to so let's try to find the normal stress. Find the normal stress at point B. Right, so it's very similar to what we did in the case of point A. So the first thing we do is we put sigma B is equal to sigma force plus sigma bending. And then here you're gonna have, so you have a compressive force of magnitude 100 kilonewtons, so it's gonna be a minus, please put a minus for compression plus for tension, minus W over A. This is the normal stress due to the force. And since we have double bending in here, so it's going to be plus or minus mz x over iz plus or minus mx z over ix. Now we're going to determine whether these things are plus or minus, alright, and we're going to find out the magnitudes of these things in here. Now notice that point B lies on the x-axis, and whenever a point lies on an axis, then we have said in the previous video that whenever a point lies on the axis, then the bending moment about that axis, or the bending stress about that axis, is going to be 0. Alright, so in here, since point B lies on the x-axis, this means that mx over ix is 0. Why? Because point B lies on the x-axis. Alright, very important. Now, point B doesn't lie on the z-axis, and therefore this thing in here is not 0, alright, which is mzx over iz. And we need to determine if point B is under tension or compression with respect to mz. So you're going to ask yourself this question: is B under tension or compression with respect to mz? Alright, so we see that mz creates a tension region at the bottom and the compression region at the top, and since point B belongs to the tension region of mz, this means that this thing in here is going to be a plus. Why? Because point B lies in the T zone of mz. T zone meaning compression zone, and therefore you're going to have that sigma at point B is going to be minus W over A plus mzx over iz. Now W is minus 100 times 10 to the power 3 to change it to newtons. The area is 78.54 plus mz is given to be 665 kilonewton meter, so 665 multiplied by 10 to the power 6 to change it to newton millimeter, multiplied by x, which is what's x? X in this case is the vertical distance between point B. Alright, notice in here that the x-axis is the vertical axis, so x is the vertical distance between point B and the horizontal centroidal axis, which is z, so it's going to be 5 millimeters, so times 5 over iz, which is 490.87. 490.87. Again, you're going to get steps required in the process, so it's going to be 6772414, alright, megapascal. So it turned out to be positive. This means that it's acting in tension. The normal stress at point B is in tension. Alright, one more part, final part, which is step 8. And in this step, we're going to calculate the shear stress at point B. Calculate the shear stress at point B. And we know that the shear stress at point B is due to the force plus due to the torsion. Now, in here you're going to have VQ over IT plus T rho over C. Okay. Now, what is the shear stress due to the force at point B? The shear stress due to the force at point B is going to be V, which is 70 kilonewton, multiplied by Q over I multiplied by T. Now, if you look at the figure, can you tell me what Q is? So notice in here that Q, since the shear is vertical, I'm going to put this as a remark. Since the shear is vertical, this means that Q is A prime, okay, times X prime, since the X-axis is the vertical axis. Okay, this is the vertical distance. And A prime is the area above or below the point of interest, which in this case is B. It's point B. So look at the figure and tell me what is the area below point B. It's 0. That's why point B is not under shear stress due to the force. So tau of the force at point B, there's no need to calculate V, Q, IT. Just if you look at the figure, you consider point B, you should notice that the area below point B is 0. Alright, and since the shear is vertical, A prime is going to be the area above or below the point of interest, so this is going to be 0. Alright, so it's going to be, so the shear stress at point B is solely due to the torsion. Okay, so it's going to be T rho over C. The torsion is going to be 210.35 multiplied by 10 to the power 6. Rho is the radial distance between the point and the center, which is going to be 5 because the radius is 5. This is not C, this is J, so T rho over J. Okay, and J is going to be in here equal to 981.74. 981.74. Now, if you calculate this thing in here, 107.1312. Again, please, these numbers are very large, alright, they are unrealistic. Please, you're gonna see that in the following exercises you're gonna get much smaller numbers. Alright, so this is in megapascal. Now what you're gonna say about point B, what is the direction of the shear stress due to torsion at point B? It follows the direction of the torsion and it's perpendicular to the radius, and this means, so this is perpendicular to the radius, follows the direction of the torsion, it's to the left. Right, and the tau at point B is going to be to the left. Alright, so this is it for this exercise. Please review all the steps. These are the steps. I gave you a step-by-step procedure to solve problems related to Chapter 8. Recall that the numbers are unrealistic. Alright, we're going to see in the following exercises much smaller numbers for the normal and the shear stress. The normal stress is due to the force and the bending. The shear stress is due to the force and the torsion. Okay, the main takeaway of this exercise is that in the shear force due to the and the shear stress due to the force at point B, it's directly equal to 0 because the area below point B is 0. We're gonna see in later exercises, in future exercises, what to do in case you have a horizontal shear, right? So you might not only have a vertical shear, you might have a vertical and a horizontal shear, right? We're gonna solve a lot of exercises for you to master these types of problems. I'll see you in the next video where we're going to be solving another exercise. If you have any questions, please let me know, alright?